Well, we've made it to the final video of Bootcamp 1, and this is going to be a relatively short video because we're just going to review the concepts that we've been talking about in the programming module quickly just by going through some additional practice exercises. So if you're following along on the website, just go to Bootcamp 1, Module 4, Programming, and go down to where it says Practice Exercises, and that's where we're going to start. So let's go into RStudio and go through these practice exercises quickly. So again, find where in the code, in the script for this module, where it says practice exercises, and that's where we are. Here we're going to go through an example that you're probably familiar with if you've taken an intro stats class, and that is the example of null hypothesis testing. And we're going to use a made-up data set and perform a hypothesis test on that made-up data set. Let's go through it and hopefully it will make sense. So we're going to use if then else or conditional logic to perform a null hypothesis test. So we're going to make a simulated data set that has 100 samples. So we're going to say n samples is 100. Here's the simulated data. It's going to be random, normally distributed data. We're going to take whatever number of samples we specified here, it's 100, and the samples will be drawn from a normal distribution with a mean of 1 and a standard deviation of 1. All right, let's look at that. So first we'll run that line. We call this variable x, and it's going to be 100 random normal deviates. So you see sometimes it goes below 0 because we have a mean of 1 and a standard deviation of 1, so there's nothing saying that these data can't be negative. Let's look at the data using the histogram function, and we can see that we get some values as low as -2 and some values as high as above 3. The mean is somewhere around 1. And the question here we're going to ask, statistically speaking, is this mean of all these values, is the mean of all these values different from 0? Yes or no? Could this result be generated just by random chance, even if the mean was 0? All right. You can kind of speculate just looking at this. What do you think? Are we going to be able to reject the null hypothesis that the mean is 0? Well, let's find out. Let's actually run the test. So let's compute the mean. We'll call the mean mu. Oops. So the mean is, in my case, 0.882. You'll have something different because it's a randomly generated. Let's compute the standard deviation of this vector of 100 random normal deviates. The standard deviation is 1.12 in my case. And now what we can do is compute our summary statistic or test statistic for performing our hypothesis test. In this case, we're doing a t-test because we're testing whether a mean is different than 0. That's a one sample t-test. We can compute the t-statistic, which is essentially just a signal to noise ratio. The signal is the mean, the noise is the standard error, which is the standard deviation divided by the square root of the sample size. So we can compute the standard error. That's going to be, in my case, standard error is 0.11. That's the noise, that's the sampling variation that we might expect. That's the variation in the mean values that we could compute if we took different samples, essentially. That's the sampling variation. This is mu, the mean, the signal. So we have a signal of 0.88. We have a noise of 0.11. The t-statistic is the ratio of the signal to the noise, and the t-statistic is 7.9. So the signal kind of outweighs the noise. Do you think it's going to be significant? If you said yes, you're probably right, but let's run this. So the critical value of the t-statistic, that above that value, the signal outweighs the noise enough that we can kind of reject the null hypothesis. If the signal doesn't outweigh the noise, if the t-statistic is lower than the critical threshold, then we fail to reject the null hypothesis. We use the quantile of the t-distribution. So Qt is actually a function in base R that takes the quantile of the t distribution with degrees of freedom, in this case of the sample size minus 1, or 99. And we're going to do a fairly stringent test. So our alpha level is 0.025. So our p in this case is the quantile we want to get from the t distribution is 0.975. So we're only going to reject the null hypothesis if the t value exceeds the 97.5 quantile of the t distribution with 99 degrees of freedom. We can compute that value, and that value is 1.98. Of course, our t statistic is well above that value, so our signal way outweighs the noise. You wouldn't see that by random chance if the mean were 0, all right? So let's store the critical value of t, and now we can do a conditional logical statement and say, well, if t exceeds the critical value, we reject the null hypothesis that the mean is 0. Otherwise, we fail to reject. So it's just a simple conditional logical statement. Nothing really fancy here, but it's the use case that we're getting at, because we see conditional logic all the time. We use conditional logic all the time, and it's useful to be able to state this to a computer and get a computer to run through this logic. And here we can reject our hypothesis, our null hypothesis, on the basis of the observed data, including data on the mean and the amount of variation. What if the true mean were equal to 0? That is, the null hypothesis is actually true in this case. So we are going to now simulate data under a different scenario. Now that the null hypothesis is true, and if the universe is favoring us, then we should get the right answer that we fail to reject the null hypothesis. Of course, we could get a false positive, like it's possible. Maybe you will, because this is random. So let's take 100 samples from data simulated under the null hypothesis. The mean is around 0. In fact, in my case, the mean is negative 0.07. All right, and we're going to test to see if that could be generated by random chance. All right, we know it was, because there we go. It is random chance right here under the null hypothesis. But let's run through this whole exercise. We got the standard deviation. We can compute the t statistic. In this case, it is negative 0.62. Let's see if that signal to noise ratio is significantly different than what we would expect from random sampling under the null hypothesis. So the critical value, again, let's see that, is 1.98. And of course, that would be for a one sample test, but let's just go with it. And we fail to reject the null hypothesis. All right. So play around with it. There's nothing really especially new here. We're going through a really basic if-then-else statement, but the use case makes it interesting. All right. Let's go through an example with if-else, because this is a really useful vectorized form of the conditional if-then-else statement, where we can supply a vector of trues and falses, essentially, or a vector of tests. And for every one of those, we'll do something if the element is true and do something if it's false. So we can run multiple tests in one fell swoop using the if-else statement. We're going to simulate some data that has some issues, and we're going to fix the issues using the if-else statement or function. So let's first simulate some data where we kind of mess up the data entry, and sometimes we say the word detected, and sometimes we say the word 1. They mean the exact same thing, or the number 1. And sometimes not detected, and sometimes 0, but they mean the same thing that we want to fix. Let's look at this simulated data and see what it looks like. So we have a matrix. In this case, we have 3 columns, and we have 20 rows, and these are all filled in with either zeros, ones, not detected, or detected. What we would like to do is change all the detecteds to 1 and change all the not detecteds to 0. So we just have a matrix of zeros and ones that then we can subject to further analysis. So let's look at that, and we can simulate an environmental covariate that we might want to use as in a model, in a statistical model for the detection process, for instance. So the probability of detection might be greater if some environmental covariate is greater. We might want to run some analysis like that. So let's combine the response variable, that would be the observations, and the covariate, which would be habitat, so that we can combine that into a single object called data. So we have the response variable, detection, non-detection, and then we have this habitat variable. So we might want to model the probability of detection as a function of habitat. All right, so now we have a simulated data set. Obviously, not super meaningful. The habitat data is just a random normal deviate with a mean of 0 and a standard deviation of 2. So there's not going to be any meaningful signal here, but it would still potentially be a useful null data set to run through a test, because we wouldn't expect to see that habitat actually influences this process because it's completely random. It's just random noise, essentially. All right. So let's clean up the data. So what we want to do is use if-else to clean up this data set. We're going to take the first 3 columns of our data, which are just the detection, non-detection process, but we're going to run an if-else statement where we say if the data are labeled as detected, we're going to change it to 1, right? In fact, we're going to go a little bit farther. We're going to say if the data are detected, or we're going to use that pipe operator to say, or they're listed as 1 with a text string, because everything here in this matrix is a text, right? Because it are coerced all the zeros and ones to be text, because a matrix all the elements of a matrix have to be the same type, which we went through in an earlier module. And so it are coerced all the zeros and ones into characters. So now we're saying if the data are labeled detected, or if they're labeled 1, we're going to call it the numeric version of 1 without the quotes. Otherwise, we're going to call them 0. So we're going to do this if this evaluates to true, and you can look at that, it's going to be a matrix now of trues and false. So if else actually it doesn't just work with vectors, it works with matrices or arrays. And for every one of these elements, it's going to do something if true and something else if false, and it's going to return an object with the same dimensions as this vector or this structure of trues and falses. So it's going to take this, and for every true, it's going to return 1, and for every false, it's going to return 0. So this whole statement should return a matrix of zeros and ones now. So a nice simplified version where all the detecteds become 1, and all the non-detecteds become 0, and everything becomes numeric rather than character. So this is now a usable format. So we'll call that new obs. So this new obs is going to be a cleaned up response variable matrix of zeros and ones representing detections and non-detections. We can, because we added this this original data set, because this is a matrix, and everything's coerced to character, even that habitat variable, notice, was coerced to character. So we have to fix that too. So let's take the original data and we'll use the as numeric to force that covariate to be numeric again, but we see that it also has way too many significant digits, so we might want to reduce those as well. So we'll do that as well. So we'll take this new habitat variable. Now this is a numeric vector with our covariate, and now we can round that covariate we can use round essentially to specify the number of significant digits we want. So we're going to specify 2 significant digits. So if we use round with this argument 2, then we get 2 significant digits on our covariate. If we omitted that entirely, then we'd by default round to the nearest integer, all right? But we wanted 2 significant figures, so let's rerun that again. So now we have our covariate with 2 significant digits, and we can bind all these data together, and now we have a much cleaner version of our original data where the detections and non-detections are labeled properly and are ready to work with, and our covariate is numeric as it should be, and it has the correct number of significant figures. And we can add nice labels. So we'll use the column names function, which takes the column names of our matrix and makes them more readable. And so we add that, and now we have a nice cleaned up matrix that we can subject to analysis downstream. All right. Before we end, let's go through a couple more for loop examples, and then you will have time to work on your challenge problems at the end. All right. This is kind of a cool example because it's visually appealing, because we're going to take this built-in volcano data set, which basically is the elevation. You can consider this matrix like every element represents the elevation at a particular point in space. So we can think of this as kind of a raster map where each of these represents a pixel, and this is the elevation of that pixel. Okay, you can read more about the volcano data set if you just do $volcano, and you see that it's the topographic information on Auckland's Maunga Wau volcano. There it is. Read more about it if you'd like. But what we're going to do is just visualize the relief here. First of all, we're going to exaggerate the relief so that it looks more impressive in a visualization. So we're going to multiply the elevation by 2. That's going to be assigned a variable called z. Z meaning in a space you have an x and y coordinates, but now we're going to add a third axis, and that's going to be called z. So we're going to have z coordinate representing elevation, x and y coordinates representing location. X and y coordinates will be, we're going to assume that each coordinate is basically, each pixel is 10 meters wide and 10 meters tall. So we're just going to multiply the number of rows by 10 and get an approximate location or x coordinate and y coordinate. So we're going to, this is like a 10 meter spacing grid essentially. Maybe that's the actual, yeah, so this is a 10 by 10 meter grid. So it even says that in the help. So we're correctly designating the coordinates, the x and y coordinates. All right, so let's look at the z. We can uncomment that and see, does that look right? Yeah, it looks right. There's some topographic relief here, and we can try to visualize this topographic relief. So let's do that. So first of all, we're going to set the background color of our graphics window to be white. In this next line here, I see an error, because what this is going to do is going to set a single panel but too wide, because when we add this matrix to the layout function, this would just add the same plot but to a wider, I don't think this actually really does anything, to be honest. I think what we really want is to make 2 panels, and so we want to have 2 panels side by side with 1 row. So we're going to have the first panel here, second panel here. I will try to fix that in the future version of the code there, but there you go. Let's run this layout function, and what we're going to do is we're going to use the perspective or persp function here in base R, which is a function for plotting a 3D figure. And so you give the persp function x coordinates, y coordinates, and z coordinates, plus a whole bunch of other parameters. I won't go into great detail about that. We're going to manipulate the angle of the viewing angle, and we can even animate basically the topographic relief map across different viewing angles, so we can see the volcano from different angles, which is kind of cool. That's what we're moving towards right here. So let's run this first perspective plot or 3D plot, and it's going to look like this. Did I run the layout function? There we go. So now we're going to have two panels side by side. I can make the plotting window a little bigger. All right, and now we're going to change the value of theta from 135 to 90. That basically changes the viewing angle. If you want to read more about how perspective plots work, you can do %persp and learn more about 3D plots. But we're going to just change this value of theta, so just bear with me. Know that theta is going to change the viewing angle, and we can see that now we have a different viewing angle of the same volcano. The same data are being viewed, but just in a different way. All right. Now what we can do is I'm going to get rid of the graphics device for now. So say graphics off. Everything. Another way to do that is to just click on this plot broom, which basically removes all the graphical device that has been viewed, in the previous code. So you start fresh, basically. All right. So graphics off, and then we're going to use a for loop. And let's just walk through the for loop. Like I said, the good way to walk through the for loop is to set the iteration variable equal to something. It doesn't have to be 1, but oftentimes you set it to the first element in the iteration vector. So that's 1. So we'll pretend we're right at the beginning of the for loop. And so I is 1. So what we're going to do is we're going to make a perspective plot. And you see where the I enters. So theta is going to be influenced. It's going to be changed every time we go through this for loop, because the for loop, is going to iterate through I. I is going to be 1. I is going to be 2, so on and so forth. Every time, that's the fact that I is changing is going to change this theta parameter, or the angle of viewing. So let's view the 3D plot, see what it looks like. And we're going to have the for loop print out what iteration we're on. What theta is actually, is what it's going to print. In fact, if we wanted to, we could make that more explicit by using the paste function and say, and that's just going to create a text string that will include the new value of theta, but we can say theta is, and then specify what theta is. So now every time R is going to print out theta is something. Oh, I missed an end. So if I run this now, and it'll just print out theta is 20, because I is equal to 1. If I is equal to 2, pretend I'm in the second loop of the for loop, the second iteration of the for loop. I can run the perspective plot. You see how the angle changes just a little bit, and I'll print out theta is now 40, all right, because now I is 2, so theta is 40. This last line of the for loop is just going to allow us to control the speed of this animation. Essentially, this pauses R and waits for something. It waits for us to click enter. When we click enter, it doesn't do anything, but it's going to allow us to control the pace of the animation. So we have to click enter, and when we do click enter, R will run the next iteration of the for loop, and then the next iteration and the next iteration. So we have control over that by clicking enter. So let's run it. Again, we can comment this out because that was just for playing around with it, but we don't need to specify I anywhere. The for loop will specify I for us. The for loop will start off with I equals 1 and all the way to go till 18. So let's try it. Let's run it. Okay, so R is paused and it says theta is 20. Let's hit enter. And R says theta is 40. Hit enter again. And we just keep going, hitting enter, and we can see how we're viewing the same volcano, but from different viewing angles. And we can just keep going until we get to 18, which basically gets us fully around the circle, and we're done. All right. That is the demo, and it's time now to work through your challenge problems. Take the time, make sure you understand these concepts. These are fundamental programming concepts. It will definitely benefit you in the future to know these things. So it's worth spending some time. Let me know if you have any questions about anything in the lecture or about the challenge problems. And that is the end of the basic R bootcamp. We're going to move on to functions and some more advanced topics in R in the next videos. I hope to see you there.